Okay, so good evening, everyone. So today we are in the week 11 problem solving session or tutorial session of the NPTEL course, Genetic Engineering Theory and Application. So I hope all of you have gone through the week 11 lectures. Okay, so in week 10, I had skipped two parts that were covered in the lecture. One is the mass spectrometry and another is the IR spectroscopy. So in today's lecture, we will go through those parts and we will discuss questions related to those sections that will help you understand the concept and solve the assignment questions as well. So we were discussing about the different spectroscopic techniques by which we can characterize our product. So any macromolecule, biomacromolecule, whether be it protein or nucleic acid or uh, RNA, DNA, they all have a they are all unique in the sense that the amino acid sequence of one protein will not match with the amino acid sequence of another protein. Similarly, the nucleic acid, the base sequence of a nucleotide may not match with the or will not match with the nucleotide sequence of another DNA molecule. So, owing to these differences, we can we can either sequence the protein, right? So, if we directly sequence the protein, then we can characterize whether the protein that we have expressed, recombinantly expressed and purified is the protein of our interest, or we can go for some spectroscopic techniques wherein depending on the amino acid sequence, depending on the residues, charged residues or aromatic residues present in a protein, each protein will have a characteristic spectra uh, that can be utilized for understanding the behavior of a protein. So there are different spectroscopic methods, and basically spectroscopy means the study of interaction of electromagnetic radiation with matter. As we know that the electromagnetic radiation starts from the gamma rays and it goes on till the radio waves. Okay, so the gamma waves are the having the maximum energy and lowest wavelength, shortest wavelength. And as we go along the electromagnetic spectrum, the energy decreases and the wavelength increases. Or we can say that the frequency increases and the wavelength decreases. Okay, so utilizing the different properties of the electromagnetic radiation, different parts in a molecule can be excited. So, for example, when we were talking about UV visible spectroscopy, we are what we are doing, we are exciting the electrons or um, electrons which are present in the peptide bond. So the peptide bond, as you know, that it shows absorbance at around 210 nanometer, 195 to 210 nanometer. Similarly, there are depending on how many tryptophan tyrosine residues are present, a molecule will also show absorbance at 280 nanometer. So So all these the wavelength that we are using is the falls in the visible or it is not in the visible, it is in the near UV region, near UV or far UV. It is in the far UV region. Okay. Far UV region starts from 190 nanometer to around 2 280 nanometer or 240 nanometer. Okay, so let's start today's session. So I will share the slides. Yeah, so good evening again. And I am Akash Jyoti Pathak, and I am one of the PMRFTs for this NPTEL course, Genetic Engineering Theory and Application. This course is being run by Professor Vishal Trivedi of IIT Guwahati. Uh, what were the topics covered in week 11? So these are not the topics that were covered in week 11, but the topics that we will be covering today in this session will mainly talk about the mass spectrometry and the IR spectroscopy. Okay. In week 11, we have looked or we learned about the different applications of genetic engineering. So the applications part I will cover in an extra session, which I will be taking on Saturday. So Saturday there will be an extra session of 1 hour where I will discuss the applications of genetic engineering. Okay. So applications of genetic engineering, a brief idea. Whoever has taken biology in class 12 must be having that how we can utilize genetic engineering for producing recombinant or transgenic plants which are having high yields or recombinant drug products like insulin. So these are some of the common examples of how genetic engineering is being applied for synthesizing pharmaceutical products or for generation of high yielding crop varieties. Okay, but these two are these two topics were left, and it is quite important to understand these two methods. So I will be covering these two techniques today. So the product characterization, as was explained in the lecture as well, that we can characterize the product on the basis of their molecular weight, on the basis of the functional group, and on the basis of the sequence. So each molecule has a characteristic molecular weight, which can be utilized and to identify or separate one molecule from the other. So, what are the different techniques which utilizes molecular weight as a parameter for separating molecules or for characterizing different molecules? So, first one is the gel filtration chromatography. So, as we know that gel filtration chromatography separates molecules on the basis of size and shape. So, it can be possible that a molecule that two protein molecules can have the same size, but their shape or the hydrodynamic radius may be different. So utilizing that difference, we can separate two protein molecules. Similarly, and so that is the way in which GFC utilizes molecular difference in molecular weight for separating two protein molecules or separating one protein molecule from the others. Then the second is electrophoresis. Electrophoresis is separating on the basis of size only, isn't it? Because we had discussed that we add SDS to our protein, which linearizes the protein and gives an equal mass to charge ratio. So all the proteins will have equal mass to charge ratio. The only difference will be in their size. Okay. So, and the second way by which we can characterize molecules is by mass spectrometry. And here also, when we are which technique of mass spectrometry is used for characterizing products on the basis of molecular weight, that is MALDI-TOF. We will discuss about this technique, MALDI-TOF. Mass spectrometry can be used for calculating or determining the molecular weight of of a sample. It can be protein, it can be an organic molecule, it can be a It can be a drug product. We can utilize mass spectrometry for determining the molecular weight. And also mass spectrometry can also be used for determining the amino acid sequence of a peptide. So we in the last class we discussed about how Edmonds degradation, how we can use Edmonds degradation for determining the amino acid sequence in a protein. But other than this, we can also use mass spectrometry, and the mass spectrometric technique which is used for sequencing the protein is tandem MSMS. Tandem mass spectrometry. We will learn about this technique today. The and Or we can also say that another common name for this technique is also called protein mass fingerprinting, PMF. Okay. Now, molecules can also be characterized on the basis of the functional group. Okay. So, on the basis of the functional group, what are the chromophore present in a molecule? What are the function? What are the it can have different chromophore like the aromatic residues which are present in a protein. Those are the intrinsic chromophore. Then there can be peptide bond. There can be NAD or nicotinamide or these heme groups which are present in a protein. They are also chromophores which can be utilized for characterizing uh, the product. Okay, and another is the IR spectroscopy. So IR spectroscopy is a technique where we can characterize molecules on the basis of the functional group, or we can differentiate molecules on the basis of the functional group. So we will learn about this technique as well today, IR spectroscopy. So what is IR spectroscopy? So let's start with IR spectroscopy. So IR spectroscopy, as we were discussing the electromagnetic radiation, that the electromagnetic radiation starts from the gamma rays. Then following that, which is the next electromagnetic radiation, which is having lower energy, that is the X-rays. Gamma rays, X-rays, then UV rays, then visible light, then microwaves. No, then there is infrared radiation. Then after infrared comes the microwaves, and then there are the radio waves. So as we go along the electromagnetic radiation, what happens? The energy is decreasing, right? Energy along this side is decreasing. The frequency is also decreasing along the electromagnetic radiation, but the wavelength is increasing. Wavelength is increasing. Okay. So in infrared spectroscopy, we are utilizing the infrared radiation of the electromagnetic radiation. We are utilizing the energy of the infrared radiation for characterizing or for studying the behavior of our molecule. Okay. So why infrared radiation is used? So basically a molecule can have a molecule a molecule has some vibrational motions, shows certain vibrational motions, and the vibrational motions which a molecule shows can be excited by uh, subjecting it to the infrared radiation. So the molecular vibrations have an energy which is equivalent to the energy of the infrared radiation. So so when infrared rays are used, it basically causes absorption of the it results in molecular vibrations within the molecule, and these molecular vibrations can be utilized for studying the behavior of a molecule. Okay, so the vibrations in a molecule will depend on what are the functional groups present in a molecule, what is the type of bond present in that molecule, what is the strength of that bond. Okay, so because these different bond length, bond strength, then functional groups, what are the surrounding atoms present in the surrounding atoms of a particular in a molecule. That will all determine that at which wavelength will be absorbed by that molecule. Okay. So the energy range below the UV vis is the infrared region. So we know that the visible light starts from the 400 nanometer to 700 nanometer. Okay, now below the 700 nanometer or above the 700 nanometer wavelength, above the 700 nanometer wavelength comes the infrared radiation. Now the absorption of infrared light by a molecule results in a transition to higher levels of vibration. So a molecule has certain vibrational levels. Okay, it has certain vibration levels. So when this infrared radiation is applied, the energy absorbed by the molecule will result in transition to higher levels of vibration. Now, the bond vibrations. The bond vibrations can be either stretching or bending. We will see this, what is bending and what is stretching. The theory predicts that a molecule with n atoms will have total of 3n minus 6 fundamental vibrations, 2n minus 5 bending, and n minus 1 stretching modes. Okay, so we will look into these concepts in detail in the subsequent slides. But basically, what is happening is when we are applying infrared radiation, any molecule will have degrees of have basically 3 degrees of freedom. One is the or three different types of motion. One is the translational motion. Okay, translational motion. Second one is what is the rotational motion, and the third one is the vibrational motion. Okay, so a molecule can show 3 different types of motion. Translational motion. So basically, if you consider an atom present in a molecule, so an atom can have 3 different translational motion. It can either translate in the x-axis, it can translate in the y-axis, or in the z-axis. Then comes the rotational motion. So if you consider a diatomic molecule now, so a diatomic molecule can show 3 different rotational motion. One is along the x-x axis, or one is along the xy axis, another is along the xz axis, and another is along the yz axis. Okay. So there can be 3 rotational motion. And other than this, a molecule also shows vibrational motion. So the vibrational motion is how many different vibrational motion can a molecule show? So that is equal to 3n minus 6, where n is the number of atoms present in a molecule. Now, if the molecule is linear, then what will happen? It will only show 2 kinds of rotational motion. Okay. So basically, if a molecule is linear, it will show only 2 types of rotational motion. Why is it so? Because the rotation along its own axis will not result in any difference. So the rotation along its own axis will not give any other different orientation. That is why that rotation along its own axis is is not considered. So that is why a linear molecule will have only 2 rotational motion. It will have 3 translational motion, and as a result, it will have only it will have 3n minus 5 vibrational motions. 3n minus 5. Okay, let's look into this. So the fundamental frequencies observed are characteristics of the functional group concerned, hence the term fingerprint. Now, what is the functional group present in a molecule? That will also determine that what type of frequencies will be absorbed and which one will be transmitted. Okay, so the one that will be absorbed will not reach to the detector, isn't it? So as the number of functional group increases in more complex molecules, the absorption bands become more difficult to assign. A detailed analysis. Okay, we will discuss this when we discuss about the fingerprint. So let's go through the lecture slides. So yes, so the infrared spectroscopy, we are utilizing the infrared region of electromagnetic radiation to excite a molecule. Okay. Now this infrared radiation can be again subdivided into three regions. One is the near infrared, middle infrared, and the far infrared. So the near infrared region has a wavelength from 0.8 micrometer to 2.5 micrometer. The middle infrared region is utilizing or exciting the molecule with the radiation which is lying in this range, 2.5 micrometer to 25 micrometer. Now, in infrared radiation or IR spectroscopy, mostly what you will see is that the units are expressed in nu bar. Okay. So what is nu bar? Nu bar is basically 1 by lambda. So that is why this middle infrared, so it is better to remember the range of this near IR, middle IR, and far IR in the terms of wave number. Nu bar is basically wave number. Wave number is 1 by wavelength. Okay. So basically, what if you divide this wavelength 18 to 10 to the power 5. Um, so if you 1 divided by 18 to 10 to the power 5 will give you this value, nu bar. Okay. So now we say, yeah, for macromolecules or macromolecules, we are mainly utilizing the middle IR region. Okay. Middle IR region is utilized for studying biomolecules or for studying protein or other biomolecules which are present. So the infrared region of electromagnetic spectrum lies between the visible and microwave. So yes, visible and microwave, and it spans the wavelengths from 0.78 to 250 micrometer. The energies associated with molecular vibrations are smaller than those associated with electronic transitions and fall in the IR region. So IR spectroscopy therefore is used to probe the vibrations in molecule and is also known as vibrational spectroscopy. So basically, why are we using IR spectroscopy? So we are utilizing IR spectroscopy to study the vibrations within a molecule. So it is also known as vibrational spectroscopy. The molecular vibrations which are present in a molecule, the bending, stretching. Bending is what we will look at it in the next slide. So these are the different molecular vibrations which are present in a molecule, which are the bending and the stretching. So those to study those type of molecular motions, the IR spectroscopy is used. Now, infrared region is divided into three regions: near infrared, mid infrared, and far infrared. And spectroscopists use wave numbers to represent the IR spectra. And this is the convention which is followed. Now we can express it either in terms of wave number, and in terms of wavelength, or in terms of frequency. But what we are utilizing wave number as a conventional mode, which is utilized for representing uh, the the region in which it is which my molecule is absorbing. So mid IR region is the region of interest for studying molecular vibrations. Okay. Remember this thing, mid IR region 4000 centimeter inverse to 400 centimeter per centimeter. Now, yeah, as I was explaining that a molecule can have different motions. Okay. Now in three-dimensional space, an atom has 3 degrees of freedom, right? So if we consider only a single atom, then it can have 3 degrees of freedom. One is the what are those? Along the x-axis, y-axis, and z-axis. So a molecule composed of n atom has a total of 3 degrees of freedom. So if you consider that there are two atoms, this one and this one. So yeah, this atom will also show three different motions. This will also show three uh, 3 degrees of freedom. 3 degrees of freedom. That is why it will be 3n. N is the number of atoms. So this will also show 3 different degrees of freedom. This atom will also show 3 degrees of freedom. That is why the total number of degrees of freedom will be 3 into 3, which is 6. Now, out of these 3 degrees of freedom, what will happen? So yeah, that is what I was explaining. So if it is a diatomic molecule, then it will have 6 degrees of freedom. Now, out of these 6 degrees of freedom, 3 will be what? 3 will be the translational motion. right? 3 will be the translational motion, that is along the x-axis, y-axis, or z-axis. 3 will correspond to the rotational motion. Now, so for a linear molecule, it will have only degrees of freedom. Okay. So linear molecule will, along its own axis, the rotation that it will show will result in the same orientation, or it will not have any change. That is why there will be only two rotational motion, and there will be, other than this, there will be 3n minus 6 vibrational degrees of freedom. So if you do 3n minus 6, what will you get? 3 into 2. So if it is a diatomic molecule, then it will have zero vibrational motion. Okay. 3n minus 6 vibrational degrees of freedom. Now, among these 3n minus 5 for linear molecules represent the true fundamental modes of vibration of a molecule. So what are the different vibrational motions that a molecule shows? One is the stretching and another is the bending. So in stretching, again, you have two different motions. One is the symmetric stretch. So the bond length. So this is the bond which is covalent bond which is present between two atoms. Now this covalent bond can show stretching. So it can so when you excite it with a particular wavelength which lies in this infrared radiation, then what will happen? It can show symmetric stretch or it can show asymmetric stretch. Okay. Asymmetric stretch means this bond length is increasing, but this is decreasing. While symmetric stretch, both the bond lengths are showing vibrations in the same say, to the same extent. Now there can be bending. So bending can be scissoring. So bending will basically result in change in the bond angle. Okay, the molecular vibrations which result in change in the bond angle are called the bending mode of or bending vibrational motions, and the uh, molecular vibrations which results in changes in the bond length are called the stretching modes of vibration. So in plane bending, there can be scissoring, means what? That the angle that is present, that can cause or it is vibrating along in this fashion. Okay, or there can be rocking, uh, there can be wagging, there can be twisting. Now there are beautiful animated videos where you can visualize what is happening. So rocking means it is coming out of the, so in plane bending means in the same plane it is showing some vibration. Out of plane bending means it is coming out of the plane and moving to the plane. So that is out of plane bending. Then there can be twisting. So you can look at those videos and understand what are these different molecular vibration. Now a molecular vibration is IR active. Just give me a second. So till here, the points are clear, right? So basically, this is another important point which you need to understand. The molecular vibration is IR active. What is the meaning that a molecule is IR active? It means that the molecule on excitation with this IR radiation will result in a change in the dipole moment. That is, it absorbs IR radiation if the vibration results in a change in dipole moment. So there is two different techniques. One is IR spectroscopy and another is Raman spectroscopy. So IR spectroscopy utilizes for molecules which will show which are having some dipole moment. Only those molecules are IR active, while the molecules which are not having any dipole moment. Dipole moment, for example, you can consider CO2 molecule. CO2 molecule does not have any dipole moment, isn't it? So it has a linear orientation. Linear orientation. So that is why this carbon dioxide molecule, what will it do? It will use if you utilize Raman spectroscopy, uh, then it will show bands. But if you utilize IR spectroscopy, then this linear molecule will not show any absorbance. Okay, so a diatomic molecule that has one mode of vibration may not absorb an IR radiation if the vibration does not accompany a change in the dipole moment. This is true for all homonuclear diatomic molecules such as hydrogen, nitrogen, oxygen. So if we consider the hydrogen molecule, then what these are all what they are homonuclear diatomic molecules. They are having the same atom. So two atoms of hydrogen um, is making up the hydrogen molecule. Similarly, nitrogen also you have two atoms of nitrogen, which is making the nitrogen molecule. So if, in these type of molecules, there is no dipole moment, isn't it? The dipole moment is zero. So the vibration will not accompany a change in the dipole moment, isn't it? So so because it will not result in any and what is IR spectroscopy doing? IR spectroscopy is basically measuring the vibrational motions. Okay, so that is why these molecules which are having dipole moment zero will not show any vibrational motions. Or that because there is no change in dipole moment, there is it does not accompany or it will the vibrations will not accompany a change in dipole moment. So these molecules are IR negative. Or IR inactive. IR not IR negative, they are IR inactive. IR active molecules are the ones which will accompany that the vibration will accompany a change in the dipole moment. So the vibration of carbon monoxide. So now if you consider a heteronuclear diatomic molecule like CO. So carbon monoxide. So this has a difference in electronegative. So there is a difference in electronegativity between these two atoms, right? So oxygen is more electronegative and carbon is less electronegative. So that is why the vibration will result in a change in dipole moment, and hence these are IR active molecules. Okay, so carbon monoxide causes a change in dipole vibration of results in a change in dipole moment and is therefore IR active. So remember that vibration of any molecule which results in a change in dipole moment is called IR active. Now the vibration of a bond involving two atoms that have large electronegative difference is usually active, like the case of carbon monoxide. So carbon monoxide has large electronegative difference. That is why it is IR active. Now, an IR active vibration of a particular frequency absorbs IR radiation of the same frequency. Okay, so these molecular vibrations that we were talking about, like bending, stretching, these molecular vibrations are associated with a particular energy. So whenever this energy will be equal to the energy provided by this IR radiation, the molecule will uh, will absorb that particular IR radiation, and it will get excited to higher vibrational energy levels. Okay. Now let us calculate the position of an absorption band. So let us calculate the position of absorption band for carbonyl stretching vibration. Now so each of these bonds that are present, like carbonyl functional group, aldehyde functional group, CHO, carboxyl functional group. Each of these functional groups are associated with a particular vibrational frequency. So for carbonyl stretching vibrational, the vibration, the frequency that is known as 5.1 into 10 to the power 13 vibrations per second. So if you want to calculate the position of absorption band, so how will you calculate that? So you know the frequency, right? You know the frequency. Frequency is 5.1 into 10 to the power 13 vibrations per second, and absorption band will be equal to the wave number, basically. So when you want to calculate wave number, so nu bar will be 1 by lambda. Okay. Nu bar will be 1 by lambda, and you know this formula C equal to nu lambda. So you can substitute lambda and write lambda as C by lambda. Okay. So 1 by C by nu, 1 by C by nu will give you nu by C. So now you know the frequency. You know that the frequency of the carbonyl stretching vibration is known, and the speed of light. What is the speed of light? It is 3 into 10 to the power 8 meter per second. And in centimeter per second, what will be the speed of light? It will be 3 into 10 to the power 10 centimeter per second. So you can substitute these values and you can get the absorption band of the molecule. Okay. So the functional group region and fingerprint region. So if we consider a protein molecule, so these proteins have amide bonds or peptide bond. So what is the peptide bond? You know that there is a CONH. Then there will be COO minus group, and there will be an NH3 plus group. Okay. Or there will be a C alpha group basically. Then there will be this NH3 plus. Here also there will be another C alpha carbon. So what you can see over here that there are different bonds which are present in a. If you just consider, so you do not need to consider these other groups which are present. Just consider the peptide bond. So the peptide bond is composed of this carbonyl group. It is composed of this CN peptide bond. This shows a partial positive or there is a partial bond between the, so this bond is between the say double bond and the single bond. There is a partial double bond character, isn't it? Then there is this NH bond. Okay, then there will be NC bond, there will be carboxyl bond. So these different you can see here that this biomolecule is composed of different functional groups. It has a carbonyl group, it has a amide group, it has a carboxyl group. So if we consider the peptide, then it will have different bonds, and each of these bonds has a characteristic molecular vibration. So depending on its characteristic molecular vibration, it will absorb that particular IR radiation. It will absorb that particular wavelength and be excited to higher vibrational energy levels. Now, the absorption bands in the range of 4,000 to 1,500 per centimeter region helps in the identification of functional groups. Okay, then what is the meaning of this? It means that the functional group will absorb in this region, 1,500 centimeter inverse to 4,000 centimeter inverse. So this region is therefore also termed the functional group region of the IR spectrum. So this region, 1,500 to 4,000. Now you can deconvolute this IR spectra, and you can assign the peaks that which peak uh, is a result of which functional group. So there is a database. You can go through those database and you can assign that at, like here you can see that uh, around this 400 or 3,300 you are getting a peak. So this 3,300 peak corresponds to which functional group? Similarly, here you can see that there is a sharp peak at this 1,600 or 1,800 centimeter inverse wave number. So what does this, which functional group shows absorption at this particular wave number? So you can deconvolute and you can assign that which peak is corresponding to which functional group. Now, the lower energy portion of the mid IR region, 1500 to 400 centimeter, usually contains a very complicated set of peaks arising due to complex vibrations along involving several atoms. This region is unique to a particular compound and therefore is known as the fingerprint region of the IR spectrum. So this region, 1500 to 400 centimeter, 400 per centimeter, this region is unique for every biomolecule. That is why this is known as the fingerprint region. And they're useful to identify a compound if the spectrum of the compound is already known. Okay. So the most common application of IR spectroscopy is perhaps to identify the functional group. Okay, so this is possible because different functional groups vibrate at different frequencies, allowing their identification. The frequency of vibration, however, depends on additional factors such as delocalization of electrons, hydrogen bonding, and substitutions at the nearby groups. Okay, so the functional group. Why is this region unique? Or the functional group will or the absorption band or the peak at that particular wave number will be different for different molecules because the functional group will be surrounded by different atoms, or it can have there can be hydrogen bonds, there can be delocalization of electrons. All these will determine or will it will make the molecule unique. Okay. So utilizing this fingerprint region, what is the spectra we have obtained in the fingerprint region? We can identify which compound is present in the molecule. Okay, so if you are given a drug molecule and you have to characterize what are the uh, what are the different or whether it has any impurities in it or whether it is pure. So you can do a IR take an IR spectra, and you can identify that what are the that whether it has any adulteration, whether there is any impurities in the sample, or what are the excipients which is present in the drug molecule. All this information you will get by recording an IR spectra. Okay, so as I was explaining that the functional group regions have different vibrational frequencies. So the alcohols, ethers, esters, carboxylic acid, they have a vibrational frequency in this range, 1000 to 1300 nanometer. 1000 to 1300 per centimeter. So then for aldehydes, ketones, esters, carboxylic acids, the vibrational frequency is in this range, 1750 to 1680. For amides it is 1680 to 1630. For any stretching, there is the vibrational frequency falls in this region. Okay. Then for amines and amides, the bending vibrational frequency of amines and amides will fall in this region, 1640 to 1550. So you can see here that the functional group vibrational frequency. You can see here that each functional group has a typical vibrational frequency. And when this particular vibrational frequency will be applied to the or particular vibrational frequency will excite that molecule, it will show transitions to higher vibrational energy levels. Okay. Okay. So what are the different applications of IR spectroscopy? So as we were discussing just now, that IR spectroscopy can be utilized for identification of functional group. Now, once this functional group are known, then gradually we can also know the what is the molecule which is present in the sample. Carbonyl is an interesting. The stretching vibration of carbonyl group causes changes in dipole moment, consequently resulting in a very intense absorption band. Furthermore, the frequency of carbonyl stretching does not differ significantly from aldehydes, ketones, carboxylic acid, and ester. The large intensity and relative unchanged frequency of carbonyl stretching allows easy identification of carbonyl compound. So, do not have to go into too much detail of IR spectroscopy. So that is an entire chapter which is taught for people who are graduating in chemistry. But just you have to know that what is the principle of IR spectroscopy. That you have to understand that yes, we can utilize the IR region of the electromagnetic radiation to study the molecular vibrations which are present in the sample, or which is present in the compound. So a molecule can have basically two different molecular vibrations. One is stretching and bending. So, the stretching now, the stretching and bending, these molecular vibrations will only be possible for molecules which have dipole moment. Molecules which do not have dipole moment, like homonuclear diatomic molecules like hydrogen, oxygen, nitrogen. These are the vibrations will not result in any change in dipole moment, or the dipole moment of these molecules are zero. So they are IR inactive. Okay, these basic concepts you have to understand. And what are the applications? You can, as I was explaining, that there is the fingerprint region which lies between the 500 centimeter inverse to 400 to 1400, which can be utilized for identifying the. So you can see here as well that from this region 1500 to 400, that can be utilized for identifying the functional group. You can also identify a compound. So the fingerprint region of the IR spectrum is unique to each compound, and this can be utilized for identifying compound. So a patented drug, if suspected to be synthesized by another pharmaceutical company, can be easily identified by comparing the IR spectra in the fingerprint region. So what drug companies do is that they change the excipient, they change the composition. There can be a change in the, or there can be some adulteration. Those information can be obtained by recording the IR spectra of the patented drug or the marketed drug, and the drug which has been newly manufactured. Okay. Now we can also identify the impurities which are present in the sample, or present in a compound. Okay. Now that IR spectroscopy can also be utilized for studying the structural transitions in lipids, glycerolipids, glycerophospholipids, phosphatidylcholine, phosphatidylethanolamine, all these are glycerophospholipids, isn't it? They constitute the major class of structural lipids, and these lipids have structural phases. So gel phase with all trans conformation, and the liquid crystalline phase where Gaussian conformations are also present. The methylene stretching vibrations give the most intense absorption bands in lipids as expected for a molecule having long hydrocarbon chains. Both methyl stretching and bending vibrations are sensitive to the conformation of the lipid. So, different you can utilize IR spectroscopy for studying drug lipid interaction as well. So these lipids have this CH2 group, the fatty acid chains which are present in lipids. They have characteristic. They show characteristic molecular vibrations, or they absorb at they have certain stretching and bending vibrations. So you can study that how these different band patterns are changing when for example, your ligand or your drug is interacting with the lipid bilayer. So such type of information can be obtained from IR spectroscopy. Remember that carbonyl stretching vibration rise in this range, 1700 to 1750. So these are another very important application of IR spectroscopy that you can determine the secondary structure of a protein. So there are two methods of spectroscopy by which you can determine secondary structure. One is the CD spectroscopy, circular dichroism spectroscopy, and another is the infrared spectroscopy. So in CD spectroscopy, what is the source of light, or the source of light falls has a radiation in which region of the electromagnetic radiation? So it lies in the UV region, isn't it? So there are two types of CD. One is the far UV CD and another is the near UV CD. So we utilize the far UV CD. So far UV CD means the wavelength will lie from 190 nanometer to 240 nanometer. Okay. So that is where we are exciting the molecule in the far UV region. But in IR spectroscopy, we are exciting the molecule in the infrared region by applying radiation in the infrared radiation. So you can also utilize IR spectroscopy for determining the secondary structure of a protein. So what do you mean by secondary structure of a protein? It means that the that a protein molecule, if you look at the structure of a protein molecule, you will see that it is composed of different variable number of alpha helices, beta sheet, random coil, turns. So these different secondary structures gets repeated and folded um, to give a tertiary structure to a protein. So what are the how many alpha helices are present, or what is the percentage of alpha helix? What is the percentage of beta sheet? What is the percentage of random coil in a protein? So this is what we mean by the determination of secondary structure of a protein. Okay, so like CD spectroscopy, this region of interest now here. You have to understand that the peptide group results in 9 distinct bands. So how IR spectroscopy is utilized for peptide secondary structure determination? That has again a lot of uh, bands which you need to remember. So there is the amide A, B, and then amide 1 to 7. So what are the uh, different bonds? So where is the carbonyl bond? Then there is this CH amide bond, then carboxyl bond. So these are have these all these give rise to different amide regions. So those are labeled as amide A, B, 1, 2, 7. So you do not have to go into too much detail, and just you have to understand that this amide one is so amide 1 is the most useful band in studying the polypeptide backbone conformation. Okay, so my polypeptide backbone means what? So just see and NCO, that backbone region without the side chains. That backbone conformation can be analyzed in this region, 1600 to 1700 frequency. And it arises largely due to the carbonyl stretching with small components of the CN stretching and the NH bending. The frequency of carbonyl stretching vibration is sensitive to hydrogen bonding and therefore to the conformation of the polypeptide backbone. Okay. If you see here alpha helix, you know that alpha helix, there are hydrogen bonds at every n plus 4 amino acid residue. So that is why the hydrogen bond of or the depending on what the hydrogen with the hydrogen bond is being formed between which two amino acid residues, that will also determine the provide information about the secondary structure of the protein. Okay, so you can see here that alpha helix has molecular vibrations in this frequency range, 1640 to 1657, beta sheet 1623 to 1641. So basically, if you see this figure, so this is the IR spectra that you will get if you record a so if you take a protein and if you record the IR spectra, you will get this type of spectra, the black colored spectra that you see. That is what you will get. Now you can deconvolute it and you can determine that what is the percentage of alpha helix, what is the percentage of beta sheet, what is the percentage of random coil, and how are you doing that? How are you deconvoluting it? Because you know that this particular peak that you have obtained, that is in this range, that is in the range which is characteristic of the alpha helix. So alpha helix has the frequency from 1640 to 1657. So that is why this peak that I have obtained for the protein is because of the alpha helix which is present in the protein. Similarly, you are getting a peak here that is corresponding to the beta sheet. Now, random coil has these information are known. That random coil if a protein is completely unordered, then it will show absorbance in this region. If a protein is completely composed of antiparallel beta sheet, then it will show frequent absorption frequency in this region. Okay. So that is why vibrational frequency in this region. So you are utilizing that and you can deconvolute the spectra to determine what is the percentage of the secondary structures present in a protein. Now answer this question. So we were discussing that which technique can be used for identifying. So you do not have to understand the entire or what are the different regions, what are the vibrational frequencies of alpha helix, beta sheet, all this information. Yeah, you do not need to remember, but you just have to understand that what are the different applications. You need to know that yes, IR spectroscopy can also be utilized for studying the secondary or determining the secondary structure of protein, and what is IR spectroscopy, basics of IR spectroscopy. This much information is necessary. You need to, so for this question, that much information is needed that yes, IR spectroscopy can be used for identifying molecules on the basis of their functional group. So as I showed you a chart that this carbonyl functional group, amide functional group, amine functional group, carboxyl functional group, each of these have a particular vibrational absorbance, shows the absorbance at a particular vibrational frequency. And that is why utilizing that particular vibrational frequency, we can identify that what is the functional group which is present in our compound. Okay. So answer is function is IR spectroscopy. Already discussed this in detail. Second question, the molecule that exhibits vibrations which cause changes in dipole moment are considered as. So as I was explaining that heteronuclear diatomic molecules which are having a dipole moment, only they will be considered as IR active. Like here carbon monoxide. Carbon monoxide, then there can be water as well. Water is also having a charge difference, isn't it? Your oxygen is highly electronegative and hydrogen is electropositive. That is why there is a dipole moment. So molecule which show a change in dipole moment on absorbing a vibrational frequency is will be IR active. Others will be IR inactive. IR inactive examples of IR inactive molecules are nitrogen, oxygen, even CO2. CO2 is not IR inactive. Okay, CO2 has a is IR active, but because this carbon dioxide molecule shows will show some stretching and bending motions, which results in the in absorbance of particular vibrational frequencies. Yeah. So some asymmetric stretching and bending. So the vibration of carbon dioxide results in transient or temporary dipole moments. Okay. The vibrational motions within the carbon dioxide molecule will result in temporary transient dipole moments. And these temporary dipole moments interacts with the IR light and results in the carbon dioxide molecule to be IR active. Homonuclear macromolecule or homonuclear, this is not homomolecular. Homonuclear molecule are IR inactive. Why? Why are homonuclear molecules IR inactive? Because the dipole moment does not change during vibrations. Okay, so if the dipole moment is not changing during vibration, then that molecule will be IR inactive. Okay, but for carbon dioxide, the dipole moments change. Carbon dioxide, the dipole moment change during vibration. Why? Because of asymmetric stretching and bending. And because of the change in dipole moment, the molecule is IR active. Though it is having dipole moment 0, but still it will be IR active. So for carbon dioxide, the number of vibrational, what will be the number of vibrational frequencies? It will be actually 3n minus 5. You can apply that formula. So for carbon dioxide, number, how many atoms are present in carbon dioxide? It is 3. It has one carbon atom and two oxygen atoms. That is why. And carbon dioxide, we know that the carbon dioxide molecule is linear. That is why it will have a single vibrational mode. So no, not three, four different vibrational modes. It has four fundamental vibrational modes. Okay. So these are symmetric stretching, asymmetric stretching, bending. Okay. So for so if the dipole moment change during vibrations, then that molecule will be IR active. Otherwise, it will be IR inactive. Okay. And for linear molecule, you need to remember this formula that the number of vibrational frequencies will be 3n minus 5. Instead of 3n minus 6, there will be 3n minus 5 vibrational modes. The region of electromagnetic spectrum mostly used for IR spectroscopy is what? It is mid IR region. Okay. Because all your functional group and will is showing absorbance in this region from 400 to 4000. Okay. In far UV, in far infrared region, the radiation source that is used is what? It is mercury arc. Okay. You can read about these different lamps. So it is mercury arc. And the material used for calibration of IR instrument is polystyrene. Okay. Now we will move to mass spectrometry. So in the last class, we learned about how we can use Edmonds degradation for sequencing our protein of interest. But rather than Edmonds degradation or we can use another method, which is mass spectrometry. Mass spectrometry can also be utilized for determining the molecular size of a protein, or it can also give us the sequence of a protein. It can provide two information. One is the molecular mass or molecular weight of a protein, and what is the other information it can provide? It can provide the sequence of amino acids in a protein. Okay. Now, so mass spectrometry provides a highly accurate measure of the molecular weight of a protein. Molecules to be analyzed, referred to as analytes, are first ionized in vacuum. When the newly charged molecules are introduced into an electric and or magnetic field, their paths through the field are a function of their mass to charge ratio, M by Z. Okay, so basically what is done, you have an analyte. So that analyte is first ionized. Okay. So now once your analyte is analyzed, what will you get? You will get a charge. Your analyte will be converted into the gas phase. Now, gas phase which will have a charge. Okay, it will have a charge. Now, so they just first ionized in vacuum. Ionized in vacuum, when this newly charged molecule are introduced into electric or magnetic field, their path through the field are a function of their mass to charge ratio. So we will look into the different components of a mass spectrometer. So it will have a source of light, then there will be an analyzer, and then there will be a detector. So there are basically three main components. One is a source, a laser source. Then there will be an analyzer. So in the analyzer, your molecule will get separated on the basis of the mass to charge ratio. And the third is the detector. So the measured property of the ionized species can be used to detect, reduce the mass of the analyte with very high precision. Now, although mass spectrometry has been in use for many years, it could not be applied to macromolecules such as proteins and nucleic acid. Why is it so? Because in what you are doing in mass spectrometry, you are first ionizing the sample. Now, if you ionize if you ionize the if you for proteins and nucleic acid, those are biomolecules, isn't it? If you ionize it, then what will happen? Then in the molecules, basically there will be decomposition. The molecule will get decomposed, isn't it? It will have no information. The MBZ measurements are made out molecules in the gas phase, and heating or other treatments need to transfer a macromolecule to gas phase usually causes its rapid decomposition. Okay, so ionization is basically done in results in the gas phase or made of the molecules in the gas phase, and because of this, there will be rapid decomposition of the molecule. Now, to overcome this problem, two mass spectrometric techniques were developed. One is the one is the MALDI MS, and another is the ESI or MALDI TOF, and another is the ESI MS. So, as I was explaining, so this is a figure taken from the book Libler, and you can see here that in a mass spectrometer, there are three different components. One is the source of light. Now, this source of light, what will it do? So, you basically apply electric or you apply energy to your source of light, and as a result, all your molecules which are in the gas phase, they will, or the molecules will get ionized in the gas phase. And now these ions will move through the mass analyzer, and through the mass analyzer will separate the molecules on the basis of their M by Z ratio, and then you will have the molecules which will be detected on the detector. Okay, so a molecule which is having higher mass will reach the detector later. A molecule which is having lower mass will reach the detector faster. So in this way, you will have a intensity versus M by Z. A spectra you will get where you have intensity on the y-axis and the M by Z ratio on the x-axis. So it has three essential parts. First is the source, which produces ions from the sample. Okay. So how will you produce ions from the sample? You have to apply heat energy or electric energy that will convert the ions or that will convert the molecule or eject the electron from the molecule, and it will be converted into ions. Then the second is the mass analyzer, which resolves ions based on their mass to charge ratio. And the third is the detector, which detects the ions resolved by the mass analyzer. Now, as I was explaining that your molecules are ionized in the gas phase, and this is not feasible for protein molecules or your nucleic acid sample, because here what will the entire molecule will get decomposed. So one technique that was developed is the MALDI MS. MALDI means what? It is matrix assisted laser desorption ionization. So in MALDI MS, what is done? Your sample is mixed with a matrix with a light absorbing matrix. Now, after the sample or protein is mixed with the light absorbing matrix, a short pulse of laser light is subjected on the sample, and the proteins are ionized, and then desorbed from the matrix into the vacuum system. Okay, so you have your protein sample. Okay, you mix it with the matrix. Now, this matrix has particular wavelength of light that it will absorb. Okay, now once you mix it, then you apply that particular laser light of that particular frequency. Now, once you apply that particular energy, what will happen? Your protein will get ionized, or it will get desorbed from the matrix, and it will get converted into ions. Okay. Now, once it is converted into ions, it will move through the mass analyzer. So macromolecules in solution are forced directly from the liquid to the gas phase. So it was in the liquid phase. When you apply that particular light that is absorbed by the matrix, it will get converted into gas phase. Now the solution of analytes is passed through a charge needle that is kept at high electric potential. So this is the principle of MALDMS and this is the principle of ESIMS. So in ESIMS, what is done? Your sample is made to pass through a very fine nozzle and that particular nozzle is maintained at a positive potential. So when your sample will be ejected from that charge needle, it will get converted into gaseous ions. Into a fine mist of charged microdroplets. We will look at this, okay? Now the solvent which is surrounding the macromolecule that will evaporate and it will leave multiple charged macromolecule ions in the gas phase. This technique is called spray ionization mass spectrometry or ESIMS, and protons added during passage through the needle gives additional charge to the macromolecule. Okay, do not have to get overwhelmed by this. We will look into these MALDMS and ESIMS one by one. Okay, so just look at this figure. This is again taken from the book Libler. So you can see here that your protein sample is mixed with the matrix. Okay, light absorbing matrix. Now you are applying that particular laser light that falls in the absorption frequency of the matrix. And when you apply that laser light, what happens? Your molecule molecule in the liquid phase directly converts into the gas phase and gets charged. Okay. Now, after they have been converted into ions, they will move through this mass analyzer. This is mass analyzer. There can be different types of mass analyzer. One is the TOF analyzer, time of flight analyzer, and then you have the detector. Now, depending on the mass to charge ratio, the molecules will get separated and will reach the detector depending on the mass to charge ratio. Okay. Basically, a E into V, that particular electric field potential is applied to that ion. And it will also have a kinetic energy. Okay. So basically, your mass to charge ratio will be what? So if you solve this equation, what you will get? 2 EV by M root. So your time of flight will be what? Time of flight is will depend on the velocity. So your velocity or the time of flight is inversely proportional to the square root of the mass of the particle or mass of that ion. Now, this is a detector. Other than this, you can use you can use a reflectron. You can use a reflectron. Why a reflectron is used? Because there will be some molecules which are having the same M by Z ratio. Now, molecules which are having almost the same M by Z ratio, they will not get separated. So that is what you are doing. You are using a reflectron so that the time of flight can be increased, and as a result, the molecules will get separated. Okay. Now, so that is the principle of MALDMS. Okay. Now let's look at what is spray ionization. So look at this figure first. So you have a sample solution. The sample protein, for example, is present in a buffer. Okay. Now what you do in electrospray ionization is that you pass this protein sample through a very fine needle, and this needle is maintained at a positive potential at plus 5 kilovolt. Now, when this sample solution is made to, so this figure is taken from the book Wilson and Walker. So, as when this molecule will pass through this very fine needle, then what will happen? It will attain charge. It will gain charge. Now, as it will move through this mass analyzer, then this solvent molecule starts to evaporate, and the ion is now present in the gas phase, as it will move through the mass analyzer. And then, so that is what is electrospray ionization. So the ESI creates very small droplets of solvent. So you see here, there are very small droplets of sample, uh, which, uh, which contain solvent. And they have been produced by this method of creating very small droplets of solvent containing analyte is called atomization or nebulization, as the sample is introduced into the source through the fine glass. So this is the fine glass, and your sample is made to pass through this very fine glass capillary or glass needle, and as a result, it will attain a charge and it will be surrounded by solvent molecule. Now, as the result of the strong electric field acting on the surface of the sample droplets and electrostatic repulsion, the size decreases. So as it is moves through this vacuum chamber, the size of the solvent droplets will decrease, and also because of this electrostatic repulsion, the size decreases, and eventually single species of charge analyte free of solvent remains. These may have multiple charges depending on the availability of ionizable groups. So this is the only point of difference between MALDI-MS and ESI-MS is that the ions have multiple charges. Can have multiple charges in ESI-MS, while MALDI-MS will have only a single charge. So let's read the theory of this principle of this electrospray ionization. So it involves the production of ions by spraying a solution of the analyte into an electric field. This is a soft ionization technique and enables the analysis of large intact biomolecules such as proteins and DNA. So what is the electrospray doing? It is creating very small droplets of solvent containing analyte. The essential principle in ES is that a spray of charged liquid droplet is produced by atomization or nebulization. So when it is passing through this very fine needle, it is resulting in formation of charged molecules or charged liquid droplets. Okay. Now the solvent is removed as the droplets enter the mass spectrometer, and ESI is the result of strong electric field acting on the surface of the sample solution. So as I was mentioning, that is maintained at a positive potential, and once it is charged, then what will happen? It will get pulled towards the cathode or the counter electrode. The negative electrode, isn't it? Now, as the solvent evaporates in high vacuum region, so when it will pass through this high vacuum region, the droplet size decreases and eventually charged analyte remains. Ionization can occur at atmospheric pressure, and this method is also sometimes referred to as atmospheric pressure ionization. Okay, so once it is getting charged, these charged droplets will move through the vacuum chamber, and when it is moving through the vacuum chamber, the size of this liquid charged liquid droplets, the size will decrease gradually, and then it will reach the detector. So this figure taken from the book Leninger. Here also you can see that this is a glass capillary which is maintained at positive potential, and the sample which is present in this fine glass capillary, it is made to pass through this fine nozzle which is present in this glass capillary, and then once it passes through this glass capillary, it results in formation of charged droplets, liquid droplets. So as it will move through this vacuum chamber, you see that the charge or the size of this droplet has reduced, and then it will reach the mass spectrometer, and the mass will be analyzed. Is it clear? You can read this as well. The figure caption: the protein solution is dispersed into highly charged droplets by passage through a needle under the influence of a high voltage electric field. So once it will get positively charged, it will move towards the cathode, and then droplets will evaporate. as it will pass through this vacuum chamber, and the ions with added protons in this case enter the mass spectrometer for M/Z measurement. Now the B figure is shows a spectrum that is generated, and this spectrum consists of a family of peaks, with each successive peaks corresponding to a charge species increased by 1 in both mass and charge. So you see here this is 50, then there are 10. So as you move along this spectra, the along the M/Z axis, each of these peaks corresponds to an ion which is having one less charge. So from right to left, so if you move from right to left, then you can say that it corresponds to charge species increased by 1 in both mass and charge. So you will have this type of spectra, and now this spectra corresponds to multiple peaks like this, which has been shown here. Okay. Okay, now let's move. Now in electro spray ionization, it is a method which is developed by the scientist John Fenn. And here what you are doing, a solution of macromolecules such as peptide is sprayed from a narrow capillary tube maintained at high voltage, forming fine, highly charged droplets from which the solvent rapidly evaporates. So the same thing is explained here. This peptide is sprayed from a narrow capillary tube, and this capillary tube is maintained at a positive potential, high voltage, and this results in formation of fine, highly charged droplets. And as it will move, it will result in the evaporation of the solvent. Now, this is a series of gas phase macromolecule ions that typically have ionic charges in the range of 0.5 to +2 per kilodalton. These charges results from the protonation of the basic acid side chains such as arginine and lysine. Okay. So the proton molecule basically gets added. So the charge increases by +1. Now the ions are directly directed into the mass spectrometer, which measures their M/Z values with an accuracy of 0.01%. So other than this, so here Maldi TOF is a method which is used for determining the molecular mass of your protein. But tandem mass spec is the method by which you can determine the amino acid sequence of your protein, tandem MSMS. Okay, so how is it used? So basically, tandem MSMS is what you are having. You are doing two subsequent rounds of mass spectrometry. Okay, in tandem means one after the other. So how this is done? So the main advantage of mass spectrometry is what it is. It uses a very less low concentration of your sample is required. Sample concentration in the range of picomole. That is enough to determine the molecular mass, to determine the sequence. Okay, so the principle is that the material travels through the instrument in a manner that is sensitive to its mass to charge ratio. Okay, to use MSMS, now MSMS is used to determine protein sequence. Okay, the protein of interest is usually digested into short peptides by digestion with specific protease such as trypsin. The mixture of peptides is subjected to mass spectrometry, and each individual peptides will be separated from the others in the mixture by its mass to charge ratio. Okay, so you have your protein sample. Now this protein will be fragmented. How will it be fragmented? By treatment with, you will treat it with proteases. The most common protease that is used is trypsin. So once you treat it with protease, then you will get different fragments of your peptide fragments. So you will get different peptide fragments. Now these peptide fragments that we have obtained, this peptide fragment will be used for, will be made to pass through the mass spectrometer instrument. Okay. Mass spectrometry can also be used to sequence short stretches of polypeptide, an application that has emerged as an invaluable tool for quickly identifying unknown proteins. And the sequence information is extracted using a technique called tandem mass spec or MSMS. So basically, what is done in tandem mass spec? So first step is that you have to treat your protein with a protease. With a protease, it is either trypsin or it is a chemical reagent. And once you treat it with this protease, your protein will get hydrolyzed into mixture of shorter peptides. Now, this mixture is injected into a device that is essentially two mass spectrometers in tandem. In the first, the peptide mixture is sorted so that only one of the several types of peptide produced by cleavage emerges at the other end. And the sample of the selected peptide, each molecule of which has charge somewhere along its length. So let's look at this figure first. Okay, so you have two mass spectrometer here. So first you have fragment your protein molecule, you get different peptide fragments. Now these peptide fragments will be made to pass through this glass capillary, and that will result in formation of charged ions. And then these charged ions will pass through the first mass spectrometer, where there will be separation, and after separation, you will select a particular peptide. Particular peptide is selected, and then that will be again undergo a second round of mass spectrometry. The mixture, okay. So in the first, so that is what is explained here. Now, so for the first mass spectrometer, what is happening? The sample, each molecule which has a charge somewhere along its length travels through a vacuum chamber between two mass spectrometers. So you have two mass spectrometers in tandem MSMS or tandem mass spectrometry. Now then the second mass spectrometer is called the collision cell. Now in this collision cell, the peptide is further fragmented by high energy impact with a collision gas such as helium or argon that is bled into the vacuum chamber. Each individual peptide is broken only one place on average. Although the breaks are not hydrolytic, most occurs at the peptide bond. Okay. So you have the first mass spectrometer. So when the sample, you ionize the sample by doing a ESIMS, and then that ionized sample will pass through the first mass spectrometer. Then after passing through the first mass spectrometer, there will be separation of these peptides, isn't it? Now, from all these peptides, you select a particular fragment. You select a particular peak, and you want to see that in this peak, what are the other several peaks which compose this particular peptide peak. So then you go for the second round of mass spectrometer. So here, what happens, that particular peptide fragment or that particular peptide peak that you selected, that will be fragmented again. That will be fragmented further by a collision gas such as helium or argon, and then it is passed through the vacuum chamber. The second mass spectrometer will measure the M by Z ratios of all the charge fragments, and this process generates one or more sets of peaks. When your second mass spectrometer will be again separated on the basis of M by Z ratio, and you will get one or more peaks. A given set of peaks consists of all the charged fragments that were generated by breaking the same type of bond, but at different points in the peptide. So one set of peaks include only the fragments in which the charge was retained on the amino terminal side of the broken bonds. Another includes only the fragments in which the charge was retained on the carboxyl terminal side of the broken bonds. And each successive peaks in a given set has one less amino acid than the peak before. This difference in mass from peak to peak identifies the amino acid that was lost in each case, thus revealing the sequence of the peptide. So now look at this figure here. So in this collision cell, there is again fragmentation of this particular peptide fragment, and you are getting two different ions. One is the B ion, and another is called the Y ion. So the B ions are charged at the end amino terminal, and the Y fragments that are produced, they are charged at the carboxy terminal. Okay, so the Y ions and B ions are the on the basis of what is the charge which is present at the terminal of the protein. So that is what is explained over here. This figure is again from the book Leninger. So you can see here that after proteolytic hydrolysis, a protein solution is injected into a mass spectrometer. So this is your MS1, which is the first mass spectrometer. Now the different proteins, peptides are sorted so that only one type is selected for further analysis. So now the different peptide fragments, they will be sorted in the first mass spectrometer. And this selected peptide is fragmented further. So in the collision cell, what is happening? Your the peptide fragment that you selected, that will be broken further by this method. Uh, this collision cell that was with that argon and helium gas, they will result in fragmentation of that peptide again. Now, the selected peptide is further fragmented in a chamber between the two mass spectrometers. There is again another chamber which is called the MS2 basically. Or the many of the ions generated during the second fragmentation results from the breakage of the peptide bond. So this chamber, this collision cell, in this collision cell, there is again fragmentation of that particular peptide, and that will result in two types of ion: B type ion and Y type ion. Now, depending on whether the charge is written on the amino terminal side, if it is written on the amino terminal side, it is B type. If it is written on the carboxyl terminal, then it is Y type. So a typical spectrum with peaks representing the peptide fragments generated from a sample of one small peptide 21 residues. The labeled peaks are Y type ions derived from the amino acid residues. The number in parentheses over each peak is the molecular weight of the amino acid ion. That is the molecular weight of the amino acid ion, and the successive peaks differ by the mass of a particular amino acid in the original peptide. So basically, you can see here that there you are getting different peaks. Now, this peak, the peak that you have obtained here, and the peak that you have obtained here, the uh, the the peptide that is resulting in this particular peak, and the peptide that is resulting in this particular peak differs by one amino acid. So, calculating the difference between the mass of this particular of the peptide fragment, you can obtain the amino acid, you can obtain the molecular mass of that particular amino acid. And once you obtain the molecular weight of that amino acid, then you can subsequently determine that what is the amino acid which is present in the next peak, which is not present in the earlier peak. Okay. So from here, they have reduced the sequence of the 21 amino acid residue peptide. Okay, so multi MS and ESI MS and tandem MS. So all these things are clear, right? So actually, this is not a spectroscopy course, so no need to go into too much detail, but there were some questions which were asked in the assignment and in the tutorial questions as well. So I thought of discussing it in brief. Okay. So what are the Maldi matrices? So in Maldi top, I discussed that what are you doing in Maldi top? You are mixing your sample with a matrix, with a particular matrix, and this matrix has a chromophore, light absorbing chromophore. So what are the different matrices that can be used for your protein sample? So this is a fact-based question, and you can see here. So this table is taken from the book Wilson Walker, where you can see that what are the different matrices that are used in MALDI-TOF, and which which matrix can be used for which purpose. So if your peptide is less than 10 kDa, then you can use this alpha cyanophore hydroxycinnamic acid, CHCA. If your protein has molecular weight greater than 10 kDa, then you can use this matrix, cinapinic acid. Okay. If your protein is glycosylated, then you can use the super DHB, which has this particular molecular formula. Okay. Then you can use DHB for carbohydrates or synthetic polymers. Polymers are neutral carbohydrates, synthetic polymers, oligos, or you can use this hydroxypicolinic acid for oligonucleotides. Then you can use benzoic acid for hydroxyphenylazo, benzoic acid for oligosaccharides and proteins. So now if you look at this, the options which are there. So alpha cyano 4 hydroxycinnamic acid that can be used for peptides. 2,5-dihydroxybenzoic acid. This is also used for peptides, isn't it? 2,5-dihydroxybenzoic acid. This one. This can be used for peptides as well, or proteins as well. Or synthetic polymers is basically peptides, oligopeptide or oligonucleotide. You can use this. But dihydroxy acetophenone is not in your table. Okay, so answer is option C. Okay, and then you can also use this one, 3,5-dimethoxy 4-hydroxycinnamic acid. Now, what is the relation of time of flight with molecular mass of ions in top mass analyzer? So that is what I was explaining, that when you are once you have irradiated that sample which is mixed with the matrix, then what happens? That sample gets desorbed. Desorbed means it is removed from the matrix and it gets converted into a charged ion. Now this charged ion will move towards the negative electrode. Now depending on the mass to charge ratio of that particular peptide, one peptide will move earlier, other will reach later. So all the ions will experience the same force, isn't it? So if it is your ion, it will what force it will experience? It will experience Q into E, the charge on the protein and the electric field. So you can also write it as E into V. So the potential difference between the two electrodes. So your E into V will be equal to what? It will be equal to half mv squared, because it is accelerated through that particular velocity. Okay. So now your time of flight will depend on what? Equal to distance by V. Okay. So basically your V is what? Your V is 2 ev by m. So your velocity is inversely proportional to the square root of molecular mass of the ion. Okay. That is why answer is option C. Give me a second. So answer is option C. Okay. For this question. Now, what do the heights of the peak in mass spectrum represent? So what are you getting in a mass when you're doing a mass spectrometry experiment? You are getting m by z on the x-axis and you are getting the intensity on the y-axis. So what does this intensity correspond to? So basically, it will correspond to the abundance of each isotope, isn't it? The higher the number of ions, the sharper will be the peak, or the size of the peak will be larger. Okay. So that is why it will correspond to the relative abundance of each isotope. Answer is option D. Okay. So is it clear? So that was all for today. I hope it will clear uh, some of your doubts. So if we do not have to go through the details of each of the spectroscopy techniques, but the basics, like which spectroscopy is used for what purpose. Like for mass spectrometry, we can use mass spectrometry for determining the amino acid sequence in a protein, for determining the molecular mass of a protein. Similarly, for IR spectroscopy, we can use it for characterizing the functional groups which are present in a molecule. So these type of short questions or short info or concepts is required, because other than this there are entire books of mass spectrometry, entire books on IR spectroscopy. So covering all of this is not possible, but the basic concept must be clear. Okay, so I hope everything is clear. So if there are no more doubts, then I will end today's session, and there will be a extra session on Saturday where I will cover the applications of genetic engineering. Okay. So that was all for today. Thank you.